Okay, this is section 11.1, video 2. In the first video, we talked about and kind of defined what the idea of a sequence is and how they work, um, as well as some properties that are going to help us along the way. So let's go ahead and do some examples. First thing is we want to calculate the limit as n goes to infinity of the natural log of n over n. Given the fact that we are using n's, these are considered to be the nth term of the sequence. ln of n over n is that nth term. So we want to find out whether this thing has a limit or not. Well, like I said before, we can't really evaluate this. I mean, we can, but technically you can't really evaluate this by just substituting in values of n. The idea is that you want to kind of let this become a function of x. So we're going to call f of x our nth term, but we're going to replace the n's with x. So it'll be the natural log of x over x. And the reason for that is because if we substitute infinitely large values in for the natural log and into x, what we would get is some form of infinity divided by infinity. You would get something in that general form right there, which is the form that is one of the forms you're able to use L'Hopital's rule in. Don't forget the other one is a 0 over 0 type of situation. So if we're going to use L'Hopital's rule here, which we can now apply, we're going to take the limit as n goes to infinity of the natural log of x over x. That should not be n, that should be x goes to infinity. And you would get infinity over infinity, which is what we have on there. And that's the case. We can now use L'Hopital's rule, which says that I can take the limit as x goes to infinity of taking the derivative of the numerator, 1 over x, taking the derivative of the denominator, 1, which is the same thing as the limit as x goes to infinity of just 1 over x. And as x goes to infinity, this thing is going to approach 0. And the idea is, therefore, that's what those three little dots mean in that triangular pattern, since f of x approaches 0 as x approaches infinity, then the limit as n goes to infinity of the natural log of n over n is also going to be 0. Okay, so some of the notation on here was not the best. When I got that infinity over infinity, I probably should have written it out in this fashion. Natural log of x, limit as x goes to infinity of natural log of x is infinite, and the limit as x goes to infinity of x is infinite. Okay, and therefore we can show we've actually evaluated each of the numerator and denominator separately for their limits, and we got the correct form. So that's probably the better way to write that. All right, number 2, I guess it is. It doesn't really have a number here, but it's a second example. Determine whether the sequence a sub n equals -1 to the n is convergent or divergent. Well, if you take the limit, you're going to have a hard time doing that, because what is -1 raised to the infinite power? It's tough to say. So let's write it out term by term and see what we have going on here. So if we take the first term, n equals 1, that's -1 to the first power, that's -1. If you plug in 2 for n, we're going to get -1 squared, which is +1. If we plug in 3 for n, it's now negative. 4 for n, and so on. Okay, that pattern is just going to keep repeating. It's going to go back and forth between -1 and 1. Does this approach a finite number? Some people like to say, oh yes, it does. It approaches 1 and it approaches -1, but which one is it? Well, since you can't determine which one it is, there is no finite value, there's no one finite value this approaches. Therefore, this would actually be a divergent sequence. It does not converge. The limit does not exist because the values bounce back and forth between -1 and 1. It does not approach a single value. Therefore, this is a divergent sequence. Okay, let's look at the next one. Let's evaluate this limit if it exists. So the first thing is, well, if I look at this, because I've got that alternating term on top, we know it's going to have an alternating back and forth form, but this is where one of those properties that we had on the previous video comes into play. This property is the one that says if we take the limit as n goes to infinity, it's horrible, rewrite that, n goes to infinity, and we take the absolute value of the nth term. Well, the nice thing is that -1 to the n on the top is either going to be -1 or 1. If you take the absolute value of that, it's always 1. So what we really get out of this is the limit as n goes to infinity of 1 over n, because n values here are going to be positive. So we know that that limit approaches 0, since the denominator grows infinitely large while the numerator stays 1. That's going to approach 0. And that's that property that we had from before, saying if we take the absolute value of these things and that approaches 0, then the limit of the actual sequence itself will approach 0. So therefore, the limit as n goes to infinity, -1 to the n over n is 0. And it did not ask this, but that would mean it is convergent. All right, the next couple of examples are going to get a little bit longer, but these are probably the more important ones because they develop some ideas for later. So in this example, it says, discuss the convergence of the series a sub n equals n factorial over n to the n. Okay, for those of you who are not familiar, because some of you may not be familiar, that exclamation point is called a factorial. Okay, and we will need to know what that means, so I will define that for you in just a second. But it says to discuss the convergence of the sequence. So it's kind of telling us it's convergent, and there are ways that we can look at this to determine that it's going to be convergent, and I'll give that to you at the end of the problem as well. And then the one on the bottom, that's an interesting one because it's n raised to the n power. So that's a different kind of a function. These are two different functions that we are not used to seeing that much of up to this point, if you've seen them at all. All right, let's define this thing, which is called a factorial. For those of you not familiar, a factorial is when you take every whole number from whatever you're taking the factorial of all the way down to 1 and multiply them. For example, if I were to have 6 factorial, that is defined to be 6 times 5 times 4 times 3 times 2 times 1. Okay, that is the definition of 6 factorial. Factorials only work with whole numbers. You cannot start with 5.7 factorial. That does not work. Okay, so it's only defined for whole numbers. Another key thing for us, it's the same idea, but let's just say I wanted to find n factorial. Well, now this is being done in general. Well, n factorial says, okay, I start with the first whole number, which is n, and then I multiply that by every whole number down. Well, how do I get to the next whole number? I subtract 1 from n. So I'm going to multiply that by n minus 1. And then I'm going to multiply it by n minus 2. And then n minus 3, all the way until I get down to the last numbers. It doesn't matter how many I write. Basically, it's n all the way down to 1. I'm just doing that to show that that's the multiplication chart. There's one other piece of information. This one I am not going to prove. It's a very cool and interesting proof, but I'm not going to prove it. You're just going to have to accept it unless you want to go look for the proof, which is perfectly fine. 0 factorial. That one is also defined. That is defined to be 1. Okay, I know it might not intuitively make a lot of sense, but believe me, it does make mathematical sense when you go to look it up if you choose to. So 0 factorial is 1. 1 factorial also happens to be 1. And then 2 factorial and so on, those are going to be different values. All right, so let's discuss the convergence of this sequence using some of this basic information that I just gave you. First of all, it tells us that a sub 1, based upon plugging in 1 for n, would be 1 factorial over 1 to the first power. 1 factorial is just 1. And then 1 to the first power is 1, so really a sub 1 is 1. Okay, that's an easy one. A sub 2. Okay, a sub 2 on the top would be 2 times 1. I'm actually going to write it out as 2 times 1. In the denominator, that would be 2 to the second power, which is 2 times 2. There is a reason that I am writing it this way. A sub 3 is defined to be on top 3 factorial, which is 3 times 2 times 1. The denominator is 3 to the third power, which is 3 multiplied by itself 3 times. And then I'll do a sub 4, which is 4 times 3 times 2 times 1. And the denominator, it's 4 to the fourth power, which is 4 times 4 times 4 times 4. Again, there is a reason I am writing it this way. Now let's take a look at what a to the n would be if I tried to write it out. I'm sorry, not a to the n, a sub n. Well, that would be n factorial on the top. I've kind of defined that up there in the top part there in green. So it's n minus 1, n minus 2, all the way down until we get to 3 times 2 times 1. And the denominator is going to be n to the n power, which is n times itself, n number of times. That one's really hard to write out. So it's n times n times n, all the way down until we get to n times n times n. This has to occur n times. Again, there's no real easy way to write that out. All right, so this is what we need to do. We are going to separate a portion of this. What I'm going to separate off of here is this 1 over n on the end here. So I'm going to keep it as 1 over n. I'm just going to write that out front. So I'm going to write 1 over n. And then I'm going to actually just change the order and go, it looks like a minus. I'm change the order and go up. So it'll be times 2 times 3, all the way up until we get n minus 2, n minus 1, and then n on the top. And then denominator, it's just going to be a whole bunch of more n's, n times n, till we get to n times n times n, and so on. That would, in this case, occur n minus 1 times, because that's how many of them are left. Not that that really matters for what we're going to be doing here, but that's n minus 1 times that it's going to occur. Let's make that actually look like an n minus 1. N minus 1 times. All right, so here's what we have to understand. A sub n is going to be less than this piece right here. Okay, because a sub n is the whole thing, including multiplying by 1 over n. But if I separate that 1 over n off and I eliminate that, then a sub n is going to be less than that one, because multiplying by 1 over n would just introduce another number into the denominator, making that denominator bigger, which makes the fraction itself smaller. Okay, if you're not sure about that, pause it, think about that for a second. A sub n has to be less than or equal to maybe 1 over n. Okay, because again, multiplying by all the rest of the stuff just makes it smaller than a sub n. So a sub n is going to be the smaller of the two fractions. Well, if that's the case, I know I can bound a sub n. Whoops. Oh, what just happened there? I know I can bound a sub n by saying a sub n has to be bigger than 0, because I know that a sub 1 is 1, so we know that's the case, which is less than a sub n, which is going to be less than or equal to 1 over n. And now what I can say is this. Well, I know that the limit as n goes to infinity of 0 happens to be 0. And I also know that the limit as n goes to infinity of 1 over n also goes to 0. Well, if that's the case, and because of the fact that a sub n is bounded strictly in between those two, then I know that the limit of that middle piece, a sub n, as n goes to infinity, also has to equal 0. Okay, and this is because of the squeeze theorem. So we basically just said, by the squeeze theorem, that the limit of a sub n, which was our original n factorial over n to the n power, that approaches 0. And because that approaches 0, therefore, this sequence, is convergent. That should look like a CON, and it does not. There we go, convergent. Okay, that one's a bit tougher to understand. Don't worry, you will not see anything that difficult on a test or anything like that. But I just wanted to make sure you were aware that this is how the squeeze theorem could be applied in something like this. Now, I did mention that I was going to talk about this idea of this factorial and this n to the n power. The factorial on top that's what that is called. The one on the bottom where you've got a variable raised to its same variable is what is called an iterated function. Okay, it's not exponential, it is not polynomial, it is not power function. It is called an iterated function. And iterated functions, of the functions that we know so far, are going to be among the fastest growing functions that we have. Factorials are probably the second fastest growing function that we have. And the idea behind this is because that denominator actually grows much faster as n gets really large than the numerator does, even though they both grow very fast. That's why this thing approaches 0. And we'll talk about that much, much more in detail in the later parts of this chapter. All right, last example, I think, for this video, and then we'll come back with one to finish. For what values of r is the sequence r to the n power convergent? All right, so what we have to do here is we have to take into account certain values for r, because r itself is going to be a constant of some kind. So we have to figure out what values they are. So what we're trying to do is we're trying to take the limit of r to the n power as n goes to infinity and figure out what we could possibly have. We kind of have to split that up. So if r, let's put this down here, if r is greater than 1, a number bigger than 1, like 1.7, 2, 17, whatever number you want to, doesn't have to be whole numbers, but anything bigger than 1, I am taking a base which is bigger than 1 and raising it to an exponent n. Now remember, these n values can't be negatives, they can't be roots of any kind, they're just positive whole numbers. I'm going to take it and raise it to a whole number. All that can happen is for this thing to get bigger and bigger and bigger if r is bigger than 1. If that is the case, then we would just say that the limit as n goes to infinity of r to the n is going to be infinite. That's an r. So we know that it's going to be infinity if r is bigger than 1. Okay, that one should just kind of be hopefully obvious. There's another one that should kind of hopefully be obvious. What if r is in between 0 and 1? So what if r, 0 comes first, is in between 0 and 1? Well, that means it's going to be a number like 0.7 or 0.3 or something like that. If I take a number like 0.7, 0.3, keep multiplying it by itself any number of times, it's just going to keep getting smaller and smaller and smaller. Eventually, it will approach 0. Because remember, think about 0.7. That really means 7/10. So the denominator is going to grow faster than the numerator is as we start to multiply. It's going to start to approach 0. So the limit as n goes to infinity of r to the n here would be 0. So we're going to get 0 if 0 is less than, oops, not less than or equal to, is less than r is less than 1. So the only other pieces we have to figure out is, what if r is negative? And I did not include the equal to symbols on 0 and 1 for a reason. What if r is equal to those values? Well, let's check out those first. I think those are the easier ones to do. If r is equal to 1. Well, now I've got a base of 1, but we know 1 raised to a power is always going to be 1. So the limit as n goes to infinity of r to the n, because r in this case would be 1, that's really just 1. That's a constant, so that's going to be 1. If r is equal to 0, well, then I've got 0 raised to a number, but 0 raised to a number is 0. So the limit as n goes to infinity of r to the n would be 0. Okay, and both of those are finite values. Okay, 1 and 0. Those are finite values. So the only other thing we have to talk about is if r is less than 0. So what if r is less than 0? I take that back. We have two other things to talk about, because r is less than 0 doesn't necessarily finish it. But what if, let's say, what if -1 is less than r is less than 0? Basically, r is in between -1 and 0. So if r is in between -1 and 0, the limit as n goes to infinity. So let's think about that. So let's just take an example like -1/2. If I take -1/2 and I keep multiplying it by itself, it's going to alternate in sign. It's going to go -1/2, +1/4, -1/8, +1/16. But the values are going to continue to get closer and closer to 0, even though they are going to bounce back and forth between positive and negative values. So if this is the case, it's still going to approach 0. The last piece, this really is the last piece that we have to talk about, is if r is less than -1. So if r is less than, actually we'll include the equal to -1 in there. If r is -1, we've already done that. We've actually done -1 to the n power. We already know that that's divergent because it doesn't approach anything. And if r is a number which is less than -1, like let's just use -2 for example, when you start multiplying those together, you're going to get -2, +4, -8, +16, -32, +64. The numbers are getting bigger and bigger in their absolute values, and they're moving away from 0. They're basically bouncing back and forth between positive and negative, but moving further and further away from the 0 mark. So we would just say that the limit as n goes to infinity of r to the n would not exist. And that would be due to some kind of an oscillating behavior. Due to oscillating behavior. So what did we actually figure out from this? So anything that has a finite value as part of the limit is going to be convergent. Anything that does not have a finite value would be divergent. So what we ultimately have here, as you can see, is that the divergent pieces are here. Let's do this in black, are here and here. Which really tells us that if r is bigger than 1, not including 1, but if r is bigger than 1, then it's going to be divergent. If r is less than or equal to -1, it will also be divergent. So basically anything in between, not including -1, but in between -1 and +1, including the +1, is convergent. And it actually says that on our next page. in this box. The sequence r to the n power is convergent for any values -1 to 1, not including -1, but including +1, and it's divergent for all other values. Okay, that is a very important concept, and it's going to play out when we get into the next section as well. But that is definitely one you want to hold on to. So we will come back with a third video to finish off this idea of sequences being increasing and decreasing and so on.